So I'm continuing my discussion of metric spaces, and I'm going to. I discussed some sequences, the sequence space, and the set of continuous functions on a closed interval. Just very briefly. Another metric space that sort of comes up in particular examples is called the discrete metric space. I guess the discrete metric, where basically X can be any set, right? And the metric is defined like this. So if X is equal to Y, wait, got that wrong. So it's 1. The value of this function is 1 if X is equal to Y, and it's 0. No, that's backwards. Sorry. 0, 1 if X is not equal to Y, right? So this does conform to the properties of a metric. All its values take on real values. It's symmetric. It's 0 when X is equal to Y, and it follows the triangle identity. Triangle identity. So, I just mention it as an example. So I'm going to go over a problem. So we have a metric D, and it's definitely a metric. I want to determine, is K times D a metric? So for some K in the real numbers, right? So we want to look at the properties, right? So our first one, our function takes two elements of our space and sends it to the real numbers. So immediately, with regards to this axiom, K must be greater than or equal to 0. So we have one condition here, right? Y is equal to dyx. This is fine because D was a metric, right? So we have that this is true. So this is clearly true for any K. So our next thing is dxy is equal to 0 if and only if x is equal to y. So if we set this up and we say k dxy, if we have x not equal to y and k equal to 0, then we have kd is equal to 0, right? So that would violate this condition. So we have that k is not equal to 0. So we sort of have a second condition on this. And if we have, we also have the triangle identity for this, right? Z. So if we read an example here, So this is true because D is a metric. And if we multiply all of this through by K, this is also true, right? So our conditions must be K is greater than or equal to 0 and K is not 0. So we have for this, K must be some real number greater than 0. Right. Okay. Edit. So our next thing, we're going to see if we have a metric D, so D is a metric, we want to see what values of K such that D plus K is a metric. And we do the same thing, right? So dxy takes x and y and sends it to real numbers, in particular 0 to infinity. So say dxx is equal to 0. This means if we have dxx plus some constant, if k is not equal to 0, then dxx plus k is not equal to 0. So our function fails, right? So k so k must be 0, right? Because if it's not 0, then this axiom fails. That's about it. There's not a whole lot else you can do with this because we found from this sort of relationship, right? In order to fill the axioms of a metric, right? dxx must be 0. Okay. Okay. So suppose our set is the continuous functions on a closed interval. Right. And yeah, we want to show that that this particular function is a metric. Right? So again, x and y here are elements, are both continuous functions. So here t is the function evaluated at t. And I think we can just use the Riemann integral for this, because we're not doing anything fancy, and these are continuous functions, and this is normal. We're playing under the basic rules of like introductory calculus, right? Okay. So if we set our function equal to xt minus yt, what we have here is ft is greater than or equal to 0 for all t, right? So that's a nice sort of thing. And furthermore, so we have this, and we have a f of t dt is greater than or equal to 0, right? Because of that, right? So we want to show the triangle inequality, right? So let's just start out with this sort of thing. Z is just our an arbitrary continuous function that we've chosen. So each of these are real numbers, so we have that this is less than or equal to x at t minus yt, right? And also, right, this function is greater than or equal to 0 for all t, and that is also true for both of these, right? So right, we can integrate these functions. These are all continuous functions. We can find the integral from a to b, and this implies, our triangle inequality. T minus zt, and using properties of the integral, we can write it out as, right, doing the integral on two different functions. Whoops, whatever, I got smushed. Anyways, so that's that. Oops, clear. Okay. So next exercise, we want to show, so we have a metric dxy. This is a metric, right? Just using this, we want to show that this inequality is true. 3 plus blah 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 plus dxn minus 1 xn. We want to prove this, right? So what we can do, 1 xn, we can just start. So I'm going to call this a proof, but it isn't going to be super rigorous. What we can do is just start out with our regular old triangle inequality. And what we have here, this is true since D is a metric. And we have dx2 xn is less than x2 x3 plus dx3 xn, right? So on and so forth until we have, d blah 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 xn minus 2 xn is less than or equal to, xn minus 2 xn minus 1 plus d xn minus 1 xn, right? And then all we do is substitute this into whatever that was, this into here, this, this into here, right? So we end up with our final expression, right? It's sort of like a recursive kind of thing, right? So there's surely a better way, more elegant to show this, but this is the idea, right? We just expand this last term to, whatever, from x1 to x2 to x3, always keeping this the same until we reach this point, and then just substitute back in, and then we'll get this expression, right? And they'll, stack. Okay. And the last kind of example I'm going to do with metrics right now is just going to show the following inequality. So for D, a metric, we want to show that, if I get this right, dxy minus dzw is less than or equal to dxz plus dyw. All right. Right. So let's see. I started with dxy, and I can write this as dxz plus dzy from the triangle inequality. And then what we have here is dxy minus dzy, zy less than or equal to dxz. Okay. So what do we have here? Let me see. Huh. I can't read my notes. So I just have a bunch of arrows. My idea for this, I'm not sure is great. So maybe we'll start again. So if I say dxz, from the previous expression, this is less than dxy plus dyw plus dwz, right? I believe that's right. Yep, that's correct. And then I say dxz. Oh. Maybe I'll do this differently. dxy, okay, start with that, less than dxz. See, all I want to do is have dxy less than or equal to this sum, right? To those, right? So I can put as many between this as possible. So I can put dxz, and then I can put zw, dwy, right? So I could just call like this x1, x2, x3, right, x4, one, or, right, dwx4, right? So we've just used our previous thing, and then we just write out this as dzw less than or equal to dxz dyw. Okay, so what we have here is a true statement. So we need to show that well, this is always positive, right? This is a positive number, right? So if this is positive, right, this is equal to the absolute value, right? And if this is negative, right, we need to make a good argument as to why this is still why dzw minus dxy is also less than dxz plus dyw. And we can do this just by starting with dzw, right? So we can do all our things, put zx here plus dyw, no, dxy plus dyw, yeah, right? So that we filled in all of the intervening steps, and then we have dzw is less or minus dxy. This is also less than dxz plus dyw. So that we've shown in both cases this statement is true. So we can write that the positive or the absolute value of this is definitely less than or equal to xz plus dyw. Wow. So messy. Okay. That is all I'm going to talk about with regards to metric spaces for now. Alrighty.